It's very limited equations of motions. Where it comes from, is you have waves at the surface and also some background flow with vorticity waves and not vorticity, but small vorticity. It's not sense. Then you average about the orbit's motion and you get some force interns from the Reynolds. And this is what it looks like. I'm sure I already introduced that. First term, that's called the Stokes Coriolis force. And currently only there's this force. And then there's the vortex force, the term here. And this then we have, which is like the pressure gradient and some other gradient forces. The reason that we don't spell it out here is the relation of Craik-Leibovich and where we're taking the curl when we create electricity. At the end of this exercise, you decurl or uncurl, how they call it, or better, or you uncurl the equation and then you add the gradient force. So that's what then we have to.
So this is a single equation. No, the gap, sorry, I was confused.
These are just additional forces due to the waves.
Yeah, so this is one equation.
Yeah, also understanding waves interact with the recirculation. Disputes and so on, that would be the recirculation. We have this great language equation. And for instance, Langmuir circulation, Langmuir turbulence. This is a famous example. You see the sketch you might have seen. There's wind, there's waves, there's Stokes drift, and then this vortex force generates these overturnings of Langmuir cells. This is simulation turbulence. And you see the cells are not just cells like this, but they are kind of chaotic and they mix somehow. And this is Langmuir turbulence. Of course, you want to have this in climate model. You want to have this effect, this mixing effect, because in which they are in the climate model is important because that's interface to the atmosphere. It's where the atmosphere feeds the ocean. And the problem is that we have no observational evidence or tank lab experiment. There's nobody would supply that evidence. And our idea was, okay, maybe they are not correct, these equations. We want to check them. And for that, we have this two-phase model. Different polarizations. We also simulate the air and the water at the same time. And these are the equations of motions, the classical ones, of course. Some linearity. The density here is basically constant, but air density in the air phase and water density in the water phase. You see a section in this vertical coordinate, this is some horizontal coordinate. Water density is like 1,000 and air density is like 1. And technically, you define the C parameter here, which goes from 1 to 0. This is basically density. And there's this interface which very sharp gradients. And if you do many gradients are seen out in the simulation. So what people can do or different methods, we are using this Billiard diffusive model where you have a tendency equation for the C or for density basically. And this term on the right hand side, that's the Billiard magic, which kind of tries to preserve the interface by introducing some negative viscosity to make it sharp or to keep it sharp as interface. That's basically the idea. There's much more behind it, behind Billiard. There's and incorporate capillary effects, surface tension, so, and this would be the infinity or something that doesn't have our purpose here. We just want to have a stable interface. So some way to do this. The model is initialized with the linear wave solution in U and in W here. You see these orbital motions. This is a interface with some small but not too small elevation of amplitude and orbital motions. And you see here in water and in the air phase, amplitude is the same, but U has phase shift between air and sea. And we only initialize the water, but the air phase established its own orbital motion also. Looks similar to what Mark found in the air and the tank. we have no wind. That's the case. The atmosphere is just acting. Then we have different domains. A 2D domain, which started at 1 meter up to 8 meter. This number of grid points, and also try to do this in 3D, because one reviewer said, okay, it's all wrong because it's only 2D. You do it in 3D, almost do this then. And quite a large number of grid points you need to have this sharpening. Then periodic boundary conditions in X and Y, horizontal, and fixed or rigid lid at the top and at the bottom. The domain is 1 meter high. You don't see most of the domain. We only focus here on the S interface because that's where it happens. Okay, here are, then we also have trajectories in the model, and you can calculate the Stokes drift from these trajectories. There are some examples, right? You will get the surface at some point, and then you have these orbital motions which decay away from the interface with their amplitude. They are opposing anti-clockwise in air and clockwise in water due to the space shifting. And this is when you average the velocity of the parcels. Red line or black line is instantaneous, and you need a lot of parcels to get the correct red line here, which is the theoretical Stokes drift, which Jussi already introduced this formula, and the parcels they make similar thing. So our Stokes drift, which we estimate is close to 3. There's also a small vertical component, but very much smaller. It's like this the amplitude 1 centimeter per second, and this is much smaller. It was an even theory. Okay, and then we went on and tried to come up with estimates of the forcing. In the model, we have this equation, just the Reynolds stress here on the right hand side. If you keep the Coriolis force and the Craik-Leibovich equation, it looks like this. And we have V and U, and the Stokes Coriolis force in the second component. And in the two-phase model, we now take the average in X, like Reynolds average of this one, Reynolds stress, and then CS. And we get a Stokes drift or Stokes Coriolis force. This is the here shows this average Reynolds stress, both in the atmosphere and in the ocean, on the face of the water and the air phase. The red line is theoretical. The green line is the theoretical. We cannot differentiate right, between the Stokes Coriolis force from the model simulation and the theoretical value. And this is only for this time here, which is this crossover that we are in the red line. If you do it for other times, Stokes average Reynolds stress, which is the red line, looks like this, like 1 minus cosine function. If you average, then it's the green line. This times S, which is almost the same. But the Stokes Coriolis force has this variation in time. But this is what we expect from this equation from Hasselhoff. So if you use the linear solution for the use here in the second order meridian velocity equation, and we have the Reynolds stresses from the linear solution, which you know, and you can fit in all the motions. And this is when you get them after the calculation with 1 minus cosine behavior. So it's exactly what we expect. Almost exactly, you see at the end of this wave period, you see that small deviation. And this is the onset of inertial oscillation, which I want to share also explain how that works. These equations will be the Craik-Leibovich equation without any horizontally average, right? They only have the Coriolis-Stokes force in isolation, and that would be the theoretical Stokes velocity. And in our model, we don't have the real Coriolis parameter, we have it artificially enhanced, such that the initial oscillation have shorter period, right? Otherwise, we have to run the model for days. But we can only run the model for a couple of periods, 20 wave periods here. This is like 20 wave periods, and longer would take too much time. And also, the interface gets then stopped. Here you see the up and down of the interface, and this interface height is also changing slightly in time due to numerical effects. But if you use this dashed line here for the zeta here, and come up with a simple model like this, then the dashed line or the solid line, And the other line is then the one results, and you see this inertial oscillation. Right? And the anti-Stokes flow. And everything is as expected. So there's no surprise, basically. There's a Coriolis-Stokes force. And initially I didn't believe this, actually, because I'm always teaching that Coriolis was only important for waves on scales longer or comparable to the Rossby waves. That's what we say. And these surface waves are so short, they shouldn't be influenced. But if you wait long enough, then Coriolis force has an effect. Exactly this. So this is all correct. And then we went on and asked ourselves, is vortex force correct? And spoiler, it is, of course, even better than we thought. So what we did is we put some mean flow, such that we have a little math equation, Craik-Leibovich equation, this term, which is then Coriolis-Stokes force. There's no such force in the U component because we only have Stokes drift and wave direction, the x direction. But in the second moment equation, we have this effect. This also drops when we have no y derivative, but in x we can introduce some changes in the mean flow, on the background flow in the water, and this is what we did. This kind of mean flow was added to the initial conditions, and note that the amplitude, or the epsilon here, is the same amplitude as the orbital motions. It's the same magnitude, and but the variation in x is smaller. And this is one assumption in the Craik-Leibovich equation, that the variations in background flow or vorticity, which are the gradients, right, is all epsilon square and not the same all as orbital. So this we weigh here with our background flow. And then we made the one domain also larger, 8 meters instead of 1 meter. Then we can take averages over meter length and then take common differences to estimate this term here, both in the two-phase model and in this Craik-Leibovich equation. And this is showing the two which you have to compare. There's virtually no difference. This line here is the same thing at 5 centimeter depth here. So red and blue line are always instant. This background flow vortex force is exactly correct. We also did some experiments with a B component, so Y component in the background, which is order 1, then nothing is changing. And also when we have very rapid changes on the same order as the origin motions, then vorticity gets also order 1. But there was no difference. Vortex force is still good. But then, of course, you can argue this is the cross flow background velocity. It has no impact on the waves and on the vortex force. This may be an artificial experiment. So we also added then some flow in the U component of background flow in x direction with vertical shear. See, there's a Z dependency. Z dependency is order 1, and with this order 1 of the amplitude, you still get order epsilon square vorticity as Craik-Leibovich is assumed, and this is the result here. It's under Reynolds stress or the Coriolis vortex force Craik-Leibovich equation. We cannot Z at 5%. And the other curves here is where we now go further, but we want to test the system and for different background flow. Here, first example is one where we also add vertical shear and the cross propagation direction. Still all epsilon is a blue curve. There's one way we get deviations, where we see the first deviations where we have order 1 vertical shear and the long propagation blue flow direction. So there you see a little bit of change, right? And also, if you add vertical shear or epsilon in both the long and cross propagation direction, you also get some shear signal. But you see the difference is like 5% or 10%. So even if you violate the assumptions in Craik-Leibovich and go to order epsilon vorticity, like this example here, we only lightly change the vortex force, and that gives us confidence that the vortex force is very good approximation, even with the shear at flow or even background flow as well. So we can use it. There were always debates about if this is really a good idea, but I think we can do based on this own diagnostic. And then the last, the remaining force is the Bernoulli head. And there's a complication with the Bernoulli head. We will on that for the remaining time. There are different versions of this pressure. Phi is the pressure gradient or the potential and pressure gradient and gradient force. And there are different papers here in Holland. There's a fundamental paper on that. This you have to know what the P is. That's what papers by Williams. He also never said what P is, but he is talking about the mean pressure. And also there's residual, right? And they say it's the thermodynamic mean pressure, what that means. It will play a role. But it's difficult to say it. It's not. I don't want to blame anybody that something is wrong, but there's an issue, and I will tell about that. The correct version, I think, is this version from Langmuir. Where it was an error, but that is the version where you apply generalized Lagrangian mean to get your equations of motions, and that also gives you the pressure. In the Craik-Leibovich derivation, as I said, you don't get the pressure gradient because you go over the velocity gradient, use the pressure gradient. But the GLM derivation, if you know the Lagrangian mean derivation, use the pressure everything is no velocity. So you know the pressure that's in this space. And in UL, that is not a prime, but an L because it's the deviation from the Lagrangian average velocity. If you call it better. And our idea was, of course, to estimate the phi. And we set up an experiment where there is no horizontal gradient again, also no risk force. And W is 0, U bar is also 0, bar 0, everything is 0. And the vertical component of this momentum equation boils down to that. Right? And then we can look at the two-phase model where the vertical component of the equation of motions goes like the Reynolds stress here. And you can write it like the effect of the Reynolds stress is then W prime means deviation from the medium, and T bar also means the medium. The left figure shows the analysis in the two-phase model. The blue line is the residual of pressure gradient and buoyancy force, this one. And that is the term which is balancing that in the two-phase measure. The black line is what the two versions have as correction here. And if you would now interpret this P bar as a mean pressure, that would be inconsistent to one results. Because there's no room for this black line. There's no deviation between that. So it must be some other pressure, you don't know which one. Could be, we tested also this version here with the Lagrangian mean pressure, but then we have to integrate your trajectories and average the pressure along the trajectories, and then take the vertical derivative, then introduce error, and the error is the spread of the plots. Try to reduce the error by using more trajectories, use 3 millions distributed at the interface, but that didn't help so much. So we average this result in the box to get a better pressure, and then at the end you get the blue line, which is still spotty, but it matches the P, which is the the Lagrangian square of the Lagrangian deviations. And but it's hard to tell if there's a difference between red and blue, which would match this term here. So it's either there or not, we cannot say. That is the limit of the simulation, of diagnostic of the simulation. So these are my conclusions. We have on the talk, but conclusions about what we found from this model. The Coriolis force is completely consistent with the two-phase model. And of course, Hasselmann was right. That was wrong. And the vortex force also holds even beyond the limits of this approximation. So even if you go beyond epsilon square background electricity, you have some deviations, maybe of 5–10%, but the thing doesn't get completely wrong, right? It doesn't explode. So you can still use this as good approximation, even if the limits are reached. And we have the Bernoulli head. There was a complication. Here's the version from Williams. And this pressure P0, which they call actually P0, is not the beam pressure. This is for sure. This is what we found out. We don't know which pressure they meant. Also, we don't know the role of this term. But we know that this equation, this setting of Langmuir within GLM, is consistent with all the time. Okay, this is maybe just a side remark. There wouldn't be any effect, or there is no effect actually in any model. Gradient force doesn't play a role. Right? What's important is vorticity. And if you take vorticity, any gradient force goes. So it doesn't matter which phi you talk about. It doesn't matter except maybe for boundary condition. You have to say what pressure is. But that's the reason that Holden never cared about. But there's a caveat. If you talk about this turbulence conversation, then it becomes important for the pressures. Then I want to sketch this for you. Turbulent closures are often based on the turbulent plane energy equation, which is this one times square half. That is called turbulent plane energy, and it comes from this Reynolds decomposition of the wave averaged equations into mean and turbulence. Possibly, right? We have this turbulent decomposition, but we don't have turbulence anymore. We only have wave averaged and turbulence, which is anyway. We make the average 2 marks. But we don't have the wave thing. Anyway, but we have this invariance decomposition, and then we write down your equations with the vortex force and when we have limits, right? And the Craik-Leibovich equation. This is the correlation with the vortex force. This is what you usually get without any wave effect. That's the shear production term, right? Which produces turbulent energy if you put a down gradient calculation for this turbulent flux. Then with diffusivity or viscosity, turbulent viscosity, which depends on your TKE level, right? And that then is proportional to the TKE. And this way you can close your turbulence. This is the trick in turbulence dollars. But we also have these two terms. That's the correlation with the event, and that's the correlation with vortex force. We can try the two different versions of the event. This is the version which was by Williams in a later paper, also by Harcourt, where many of these Langmuir factorizations are based on. And they use this term, and there's a correlation with this term, which we didn't, which we don't have in the other one. And that gives you this correlation here with on here. And if you combine this with this form here, by product rule, you can eliminate the first part of the product rule of this term, and the other one transforms then to this shear production term within the Stokes curve. So it's like a trick, right? And then this term, the shear of the Stokes curve looks like this term with the normal production rate. And that's then welcome because now you can also use the downgraded compilation here, and then the reduction of turbulence by this Langmuir shear production parameterization. Right? That's the idea. But it's only there because you have this term. If you use this other form, which is the correct form, I think, then we don't have any correlation with the mean flow. It is UL, it's a deviation from the orbital motion, and we don't have for the mean of the wave average equation. We don't think that there's any correlation, and also the Stokes curve, we have no correlation. What you have to do is you have to expand the Lagrangian average pressure, also the UL, some way which we did here with the leading order, with the size, the deviations of the parcels in the orbital motion. The first order correction in GLM theory to get to relate this to the leading mean pressure. And if you do this also for UL, then you get some cancellations, details are dropped here. But you see, there's no bar here. For this term, U is present. And then you also have not this correlation, and you don't have this correction. And what you have is the pure form of the vortex. That does not look like this shear correction term. It's not involving the shear of the Stokes curve, but the shear of the momentum flux. That still doesn't matter. If you come up with this downgrading parameterization for the U prime, W prime, put this in, then this first version, which look like this. This is the shear production term, you're always positive. This is the Langmuir shear production term, which is also in positive direction is correct. But the other form looks like this. But you can transfer the other form, of course, by playing games and moving something in the divergence, right? Then again, you have this term here on the right-hand side, which you want to have, which Park will also have, right? So we can play games, and everything is equivalent, right? And what we did is we did an NES simulation with vortex force and different versions of the Bernoulli. These are the different versions, right? And what you find is doesn't matter, right? Bernoulli doesn't matter greater shares as you did this before because it's vorticity which matters and not the radial force. So everything is the same. And this is the shear production term, the normal one, right? This one is positive, it's negative, but the sign is wrong. So we produce energy at the base of the base layer and the surface. And these are the two versions of these other drugs, the Stokes force. And this is the Stokes shear force, and this is the other one, which is much smaller. And it's still, everything is correct, right? You can play games, move inside the divergence and move out, and everything stays the same as the result of the list. But more at this point, you want to construct a parameterization, right? And parameterize this term and more that term, and keep the flux divergence the same. The parameterization of the flux divergence the same. You make that. This is the point where the Langmuir parameterization gets have problems, because with different versions here, keeping all the same, all the other terms the same, we need to have small changes in the parameters. Then they need to be revisited. Thank you very much.